Good afternoon, everyone. So we'll be starting with the third chapter with respect to your JEE Mains 2024, right? So we'll be starting with the part one of the third chapter, that's magnetism, right? We'll be discussing some of the important questions and the PYQs as well, and we'll be dealing with the concepts of the magnetism through these questions. So we'll be starting with question number one. The question number one is that question number one says that find magnetic field due to infinite length wire at point P, right? We know according to Boyd-Savart law, right? According to Boyd-Savart law, the magnetic field due to a current element, right? That's TB. It's given by mu naught I TL sin theta upon 4 pi r square, right? This is the basic equation, basic law to calculate the magnetic field due to an element which is carrying some current I, right? The length of that element is dl, and current flowing through that is dl element is I, and theta here is the angle between the current element and the point and the line joining the point where the magnetic field has to be calculated, right? And r is the distance between the current element and the point P where the magnetic field has to be calculated, right? So when we have a finite length of current, right? When we have a finite length of current like this, finite length of current, and let's suppose this is the point P, this is the point P, and the current I is flowing through this, right? This is the point P, and the current I is flowing through this. Then at this point P, the magnetic field due to this current carrying wire, finite current carrying wire. Let's suppose this angle here is phi 1, and this angle subtended by the lower end of this wire is phi 2, right? Then the magnetic field P, net field at this point P, is nothing. It's given by the Boyd-Savart law. That's mu naught I upon 4 pi d sine of phi 1 plus sine of phi 2, right? Sine of phi 1 plus sine of phi 2. So this is the general equation, or we can say it's the general expression to calculate the magnetic field due to a current carrying wire at some point P, right? Where phi 1 is the angle subtended by the upper end of this wire, right? Phi 1 is the angle subtended by the upper end of this wire with point P, right? Let me call this as A and this is B, right? So if any such cases arise for a finite length of wire, right? For a finite length of wire, if we have to calculate the magnetic field due to that finite length of the wire, it will be mu naught I upon 4 pi d, where d is the distance between, it's the distance between point P and the wire, right? It's the distance between point P and the wire. Then the magnetic field will be mu naught I over 4 pi d sine of phi 1 plus sine of phi 2. This will be the total magnetic field at this point P because of this finite current carrying wire having the current I through it, right? Having the current I through it. Now the value of this mu naught is nothing. It's 4 pi multiplied by 10 to the power minus 7. So this is the magnetic permeability, right? Or we can say permeability of free space, right? So this is how we can calculate the magnetic field to the finite length of wire, right? But in this case, in this question, you can see we have a wire of infinite length. We have a wire of infinite length. It extends to negative infinity in the downward direction, and it extends to positive infinity plus infinity in the upward direction, right? So it's an infinite length of wire, right? Infinite length of wire. Now you can see here, this is the same situation. This is the point P here, this is the point P, and at this point P, we have to calculate the magnetic field due to this infinite current carrying wire. So at this point P, due to this infinite current carrying wire, right? What we will have to do, we can use this equation because it's a current carrying wire, mu naught I upon 4 pi 2 4 pi d sine of phi 1 plus sine of phi 2. Now phi 1 is the angle subtended by the upper end of this wire, and phi 2 is the angle subtended by the lower end of this wire. Now you can see here, since upper end extends to infinity, it means that to look at the upper end of this wire, we have to actually see parallel to this wire, right? We have to actually see parallel to this wire. It means that the angle subtended by this point P for this infinite wire, right, which is extending to infinity to the plus infinity, then the angle phi 1 here will be phi 1 here will be equal to 90 degree, right? In the same way, the angle phi 2, if it is extending to negative infinity in the downward direction, then the phi 2 also has to be equal to 90 degree, right? 90 degree each. So it means that due to infinite length of wire, the net magnetic field will be, I will be using this equation, that's P is equal to mu naught I upon 4 pi d, right? 4 pi d sine of 90 degree, right? Plus sine of 90 degree. Now sine 90 is 1, 1 plus 1 will be 2, it will be 2 times mu naught I upon 4 pi d, right? 4 pi d, 2 and 2 will get cancelled, we'll be left with mu naught I upon 2 pi d, right? Mu naught I upon 2 pi d. So this is the net magnetic field because of this infinite current carrying wire, right? Due to this infinite current carrying wire, this is the net magnetic field at this point P. So this will be the net magnetic field at this point P, right? So this equation is a very important equation with respect to the current carrying wires subtending an angle phi 1 and phi 2 by the two ends of the wire at this point P, right? Now, another question here is the similar question on the same concept, right? Find the magnetic field due to given wire at point P. It's almost a similar question, right? But now at this point, you can see here that now at this point, the upper end of this wire extends to plus infinity, but lower end of this wire is a finite, right? It does not extend to infinity. It has a finite length, right? From this point M, right? It has a finite length in the downward direction from this point M, and in the lower point L extends and or subtends an angle of theta here, right? Subtends an angle of theta at a distance of t from the wire, right? But upper end is extending to infinity. It means this angle subtended by this point P with upper end of this wire will be 90 degree, right? Or we can say sine of uh, phi 1 will be equal to sine of 90 degree, right? And lower end subtends an angle of theta. So sine of phi 2 will be sine of theta here, right? Sine of theta. Now, the net magnetic field at this point P will be nothing. It will be mu naught I upon 4 pi t, right? Sine of phi 1, that's sine of 90 degree, right? And sine of phi 2, right? That's sine of theta. So the net magnetic field at this point P will be, that's mu naught I upon 4 pi t. Mu naught I upon 4 pi d. Sine 90 is 1, right? Plus sine of theta. So this will be the net magnetic field at this point P because of this semi-infinite wire, which is extending to infinity from the positive end, and it extends to point L, making an angle of theta with this point P, right? So mu naught I upon 4 pi d 1 plus sine theta will be the net magnetic field at this point P, right? Now we have to find the magnetic field at P, right? Magnetic field at P as shown in this diagram. Now you can see here there's an infinite wire which is extending to infinity, and the current through this wire is actually perpendicular to the plane of this wire and uh, away from it. It's perpendicular to the plane of this wire, perpendicular to the plane of this paper and away from it. It means this dot actually represents a wire is passing through this plane, and the current is perpendicular to this plane, right? It's perpendicular to this plane and away from this point, away from this origin O, right? Now at this point, having the coordinate having the coordinate 3 comma 4, we have to calculate the net magnetic field, right? Now if we look at the direction of this magnetic field at this point, the direction will be somehow or somewhat like this. This will be the direction, right? We can use the right hand rule, right? Right hand palm rule we can use to find the direction. We can point out our thumb along the direction of the current, and then the direction of the palm at this point P will give us the direction of the magnetic field at this point P. So this will be the direction of the magnetic field at this point, right? Now calculating the magnetic field at this point P, we know that magnetic field due to infinite current carrying wire is nothing. That comes out to be mu naught I upon 2 pi d, right? This is the magnetic field due to infinite current carrying wire, right? So mu naught I upon 2 pi d will be the mu naught I upon 2 pi d will be the magnetic field here, right? At this point P, right? Now we have to calculate this distance. Now this distance is actually from this origin to this point, right? So this distance is nothing. So from here to where the distance will be nothing. It will be 3 under root of 3 square plus 4 square, right? That will be 5, right? That will be equal to 5. The magnetic field at this point will be B is equal to The value of mu naught is 4 pi into 10 to the power minus 7, right? And the current I is given as 25 amperes, right? Upon 2 pi into 5, right? 2 pi into 5. So it will be 5 multiplied by 5, right? So pi 2 pi and it will get cancelled. Will be left with P is equal to 2 into 5 will be 10. So it will be 10 to the power minus 6 Tesla, right? So this will be the net magnetic field at this point P, right? This is the net magnetic field at this point P. Now there are two wires, right? There are two wires extending to infinity parallel to each other. Two wires 1 and 2, they're extending to infinity, right? And they are parallel to each other, right? Now at this point P, we have to find the net magnetic field, right? At this point P, we have to find the net magnetic field, right? Now the current in the first wire is flowing in the upward direction, in the second wire it's also in the upward direction, right? Now if we first find out the direction of the magnetic field, right? Because of this wire one, the direction of the current will be into the plane of this paper. We'll represent it by cross, right? We'll represent it by cross. Then because of the wire 2, the magnetic field will be out of the plane of this paper. We'll represent it by dot. It means the two magnetic fields are actually opposite to each other, right? They are opposite to each other. It means that the net magnetic field will be the subtraction of the two magnetic fields, right? So because of wire 1, the magnetic field P1 here will be, that will be equal to mu naught I upon 2 pi d, right? Mu naught I upon 2 pi d, right? Now the current here is flowing, that is mu naught times 4 upon 2 pi. The distance is 1, so multiplied by 1. So we'll have 2 mu naught upon, right? 2 mu naught upon pi will be the magnetic field P1, right? And similarly, the magnetic field P2 will be here. That will be mu naught I is 6, right? Upon 2 pi, the distance t is 2, right? So from here, it will be 3 mu naught by 2 pi, right? This will be the P2, right? So the net magnetic field here will be nothing. The net magnetic field will be P net. That's P1 minus P2, right? P1 minus P2. That's equal to 2 mu naught upon pi minus 3 mu naught upon 2 pi, right? So this will be the net magnetic field, right? So from here, mu naught upon 2 pi, right? Mu naught upon 2 pi will be the net magnetic field. And the direction of this net magnetic field will be, the direction of this net magnetic field will be into the plane of this paper, right? It will be across, right? Into the plane of this paper. So mu naught upon 2 pi will be the net magnetic field at this point P, because of these two parallel wires, right, carrying current 4 ampere and 6 ampere each, right? Now let's discuss this question number 5, right? The question number 5 is says that the position of point from wire P, right? The position of point from wire P where net magnetic field is 0 due to following current distribution, right? We have to find the position of point. Let's suppose there is some point P, right? Let's suppose there is some point P, right? uh, at this point P from at a distance of x of this current carrying wire of 5i, right? The magnetic field, let's suppose the magnetic field at this point P is 0, right? Then the remaining distance will be 6 minus x, right? 6 minus x centimeter, right? The question is that we have to find the value of this x such that the magnetic field at this point P will be 0, right? These are two current carrying wires which are having the current 5 ampere, which is moving perpendicular to the plane of this paper, right? And current is out of the plane of this paper, right? Similarly, the current 3i is also out of the plane of this paper, right? So it means that the magnetic field at these 2 points, because of these two currents, will be opposite to each other, right? The direction of the magnetic field at point P will be opposite to each other, right? So we have to calculate the value of x at which the magnetic field will be 0, right? So let's suppose it means at that point P, the P1 must be equal to P2, then only the net magnetic field will be 0, because the two magnetic fields at point P are opposite in direction, right? So B1 has to be equal to P2, then only the field will be 0 at this point. Now they are infinite wires. For wire 1, it will be mu naught times 5i, right? upon 2 pi t. The distance is, let's suppose, x, right? Similarly, we'll be left with mu naught multiplied by 3I. The distance is 2 pi, and that will be 6 minus x, right? Now here you can see here the distance is given in centimeters, right? But you can see here the current, all the all the physical quantities, be it permeability, be it current, they will get cancelled out, right? So we do not need to convert this x, the x which is given in centimeter, we do not need to convert it into meters, right? So that we get the answer in meters, right? But we can use here, we do not have to change the units here. We will still get the answer of x in centimeters back, right? Because currents cancel out, permeability also cancels out, right? So from here you can see here 2 pi will get cancelled, mu naught I will get cancelled. We'll be just left with 6 minus x upon x, right? That will be equal to 3 upon 5, right? 6 minus x upon x will be 3 upon 5, or we can say 30 minus 5x will be equal to 3x, right? Or 30 has to be equal to 8x, right? So from here, x will be equal to 15 upon 4 centimeter, right? 15 upon 4 centimeter. So it will be 30 minus 5x, right? That will be equal to 3x, right? And from here, x will be equal to 15 upon 4 centimeter, right? So this will be the distance of this point P from this current 5I, at which the net magnetic field because of the two wires will be equal to 0, right? Because of the two wires will be 0, right? Now, there's a question that two concentric circular coils, right? Two concentric circular coils of radius 5 centimeter and 10 centimeter, radius 5 centimeter and 10 centimeter are placed in same plane, right? They are placed in same plane. If current 0.2 ampere is flowing in both coils in the same direction, then find magnetic field at the center, right? Now, the question is of the magnetic field due to a current carrying loop at the center, right? Let's suppose this is the current carrying loop, right? This is the current carrying loop, right? First of all, we'll try to find the magnetic field due to this current carrying loop, right? Now this is a current carrying loop, and let's suppose the current through this loop is I. The current through this loop is I, right? Now let me take a current element here. Let's suppose DL is the current element here. DL vector is the current element here, right? The current flowing through this DL element is I, right? That's I. Now we can see the direction of this DL element will be tangential to this circle, right? It will be tangential to the circle, and we have to find the magnetic field at this point P, which is at a distance of R, where R is the radius of this loop, right? Now you can see here the point P, the direction between the current element and the point P is always perpendicular, or it's always 90 degree, because we know that tangent is always perpendicular to the radius of a circle, right? So the direction, or we can say the angle between the current element and the point P, or we can say the angle between the current element or the line joining the point P is always 90 degree, right? So we can use the Biot-Savart law here. That's Tp will be equal to mu naught I dl sine of 90 degree here, right? Sine of 90 degree upon 4 pi r square. Now r here is capital R, that will be 4 pi capital R square, right? So the total magnetic field here will be nothing. We have to just integrate it on both sides to get the total magnetic field. That will be B is equal to mu naught I upon 4 pi r square, right? 4 pi r square. Integral of dl will be here the total circumference of this circle, right? That will be 2 pi r, right? 2 pi r sine 90 is 1, right? So from here, pi and pi will get cancelled, 2 and 2 will get cancelled, r and r will get cancelled. We will be left with p is equal to mu naught I upon 2r, right? So this is the magnetic field at the center, right? Magnetic field at the center. And let's suppose if this is the direction of the magnetic field, this is the direction of the current, then the magnetic field at the center has to be a straight line, right? It will be a line, it will be a magnetic field will be a line passing through this point P and perpendicular to the plane of this circle, right? And moving and it will be directed away from the center, right? It will be directed away from the center, right? So we can represent the magnetic field here by dot here, right? So circle with a dot. So this is the total magnetic field due to a current carrying loop at the center. Now the question is that, let's suppose if this is not a complete circle, if this is an arc, right? If suppose if this is an arc, right? if this is an arc, it's not a complete circle, right? If this is an arc, not a complete circle, then at this point P, we have to find the magnetic field, right? We have to find the magnetic field. At this point P, we have to find the magnetic field. Let's suppose it subtends an angle of alpha, and the current flowing through this arc is I, and the radius of this arc is R, right? Radius curvature of this arc is R. Then once again we'll be applying the Bed-Savart law, right? Once again, the angle between the radius and the tangent of this current element will be 90-degree, right? But in this case, what we'll do here is that the magnetic field integral of dB will be equal to mu naught, or integral of mu naught I TL sine of 90-degree, right? Upon 4 pi r square, right? 4 pi r square. Now from here, the net magnetic field B will be mu naught I, right? Upon 4 pi r square, right? Integral of dl, right? Integral of dl. Integral of dl. Now you can see here, let's suppose we have dl length here, right? Dl length is the length, right? This is the length, and this is the radius, right? This is the radius here, right? This is the radius. And let's suppose it subtends an angle of d theta here, right? D theta, right? It subtends an angle of d theta here, right? Now you can see here, you can see the length is always, or we can say theta here will be always equal to arc upon the length, right? Arc upon the length, right? Arc upon the length. Now you can see here the arc length of the arc here is dl, and the length here will be the radius of this curvature, radius of this arc, right? That's the radius of curvature of this arc. So the theta, d theta will be here. The d theta will be here. The d theta has to be equal to length dl, right? Length dl upon the radius r, right? Length dl upon the radius r, right? So from here, the value of dl will be nothing. The value of dl will be nothing. It will be r d theta, right? R d theta. So value of dl will be r d theta. So from here, if we have an arc of length, arc subtending angle of alpha with this with the center, with the center, right? It's subtending an angle alpha with the center of curvature of this arc, right? Having the radius of curvature r, then the magnetic field will be mu naught I upon 4 pi r square, right? 4 pi r square. We can replace this dl with r d theta. It will be r d theta. And integrating it from 0 to alpha, right? Integrating it from 0 to alpha. So r and r will get cancelled. We'll get the magnetic field as mu naught I upon 4 pi r, integrating theta with 0 to alpha. It will be alpha, right? It will be alpha. So mu naught I alpha upon 4 pi r, right? This will be the net magnetic field. This will be the net magnetic field uh, at point P, having an arc subtending an angle theta, subtending an angle alpha at the center of this arc, right? So this is how we can calculate the magnetic field to circle, complete circle. Let's suppose if alpha is 2 pi, we can substitute the angle of 2 pi here. So we'll be left with mu naught I upon 2r. That's the magnetic field to complete circle, right? That's the magnetic field to complete circle, right? Now, same is the question here. We can just conclude here with this equation, right? Finally, with this equation, the conclusion here is uh, if the complete circle is there, right? If the complete circle is there, the magnetic field will be mu naught I upon 2r, right? Because of the complete circle. But if an arc is given subtending an angle of alpha with respect to the origin or at the origin, right? At the origin or at the center, right? We can say at the center subtending an angle of alpha, right? Like this. This is an arc of radius r subtending an angle alpha, right? Then the magnetic field at this point P will be nothing. The magnetic field at this point P, we can write magnetic field at this point P, that's P is equal to mu naught I alpha upon 4 pi r, right? So this will be the net magnetic field because of this arc subtending an angle alpha, right? So you need to remember this equation mu naught I alpha upon 4 pi r, right? Now, we have to calculate the magnetic field to these two concentric circular coils, right? Two concentric circular coils of radius 5 centimeter and 10 centimeter are placed in same plane. If current of 0.2 ampere is flowing in both coils in same direction, then find the magnetic field at center. So at this point, we have to find the magnetic field, right? at this point, at the center or at this point C, we have to find the magnetic field, right? We have to find the magnetic field. I can see here in the first coil the current is moving along this direction, and at the center magnetic field will be, because the circular loop of radius r1. So first magnetic field b1 at this point will be mu naught I upon twice r1, right? Twice r1, right? Now the direction of the magnetic field at this point will be a dot, right? It will be a dot, right? And for the second circle, for the second loop, it will also be a dot here. It means it will be perpendicular to the plane, and out of this plane, right? It will be out of this plane, not into the plane. The direction of the magnetic field will be out of this plane, right? Now, for the second magnetic field, the second value of the magnetic field will be mu naught I. The current is same upon 2s r1, right? 2s r1, or we can say 2s r2, 2s r2. So the net magnetic field here will be, since both the magnetic fields are along the same direction, right? So the net magnetic field will be B1 plus B2, that's mu naught I upon 2 R1 plus mu naught I upon 2 R2, right? Now taking mu naught I upon 2 as common, right? Be left with 1 upon R1 plus 1 upon R2, right? Now from here, you can substitute the value of I, that's 0.2, and if you substitute the value of R1 and R2, so R1 and R2 has to be in meters, right? R1 will be 5 upon 100 meters, right? And R2 will be 10 upon 100 meters, right? So this is the conversion to be taken care of, right? To calculate the net magnetic field at point C. The net magnetic field to do current carrying loop at the center is mu naught I upon 2R, right? Now let's suppose we have n number of loops, right? We have n number of loops. If there are n number of loops, right? Like this. So there are n number of loops, right? Then because of this n loops, the magnetic field at the center will be mu naught Ni upon 2R, right? We have to just multiply it with a factor of n, right? To calculate the net magnetic field due to n number of loops, right? So because of n number of loops, the net magnetic field will be mu naught Ni upon 2R, right? Mu naught Ni upon 2R. So this will be the net magnetic field because of n number of loops at the center, right? Now let's try to solve this question here, right? The question is that two symmetrical current carrying rings, right? Two symmetrical current carrying rings are placed perpendicular to each other, right? We have two symmetrical current carrying rings which are placed perpendicular to each other with common center, right? They are placed perpendicular to each other with the common center. If magnetic field at the center due to one coil, with the magnetic field at the center, right? If magnetic field at the center due to one coil is P, then the net, then find net magnetic field. We have to find the net magnetic field, right? So magnetic field at the center due to one coil is P. We have to find the net magnetic field at point P, right? So the net magnetic field, let's suppose this is the coil, right? Because of this first coil, right? This is the second coil here, right? I can see the direction of this first coil, direction of the magnetic field because of this coil, first coil, it will be along this direction, right? Or we can say it will be along I cap direction, or we can say the net magnetic field because of this uh, coil one will be pi cap, right? It will be pi cap, right? And because of this second coil, it will be along y direction, right? Or we can say the net magnetic field because of the second coil will be p vector, that will be p along j cap, right? It will be along j cap, right? So the net magnetic field at this point p will be nothing. B net will be pi cap plus bj cap, right? Having the magnitude equal to b for each of these coils, right? So if we talk about the magnitude only, so net magnitude will be nothing. It will be root 2p, right? So this will be the net magnetic field at this common center of these two circular loops, right? Placed in this fashion, right? Or placed perpendicular to plane of each other, right? Now moving on to the question number 8, right? Question number 8, the magnetic induction at the center O is, right? Now we have to find the magnetic induction at the center. Or you can see here, these are not the complete circles, right? These are not the complete circles, but these are the two arcs connected with each other in this fashion, right? We know the magnetic field due to an arc. If we have an arc, right, like this, if we have an arc like this, subtending an angle alpha, then the magnetic field at their center will be nothing. It will be mu naught I alpha upon 4 pi r, right? Upon 4 pi r. So this is the net magnetic field. This will be the net magnetic field at the common center, right? I can see here because of this arc here, right? If the arc is like this, if this is the nature of this arc, right? If this is the shape of this arc, or we can say it's a quarter of a circle, right? It's a quarter of a circle. Then it will subtend an angle of 90 degree at the center, right? So here the alpha value of alpha will be 90 degree, right? If the value of alpha is 90 degree, then the magnetic field because of it at the center will be mu naught I 90 degree, that's pi upon 2, right? 2 into 4 pi r, right? So from here pi and pi will get cancelled, we'll be left with mu naught I upon 8 r, right? Mu naught I upon 8 r. This will be the net magnetic field at the center, right? Because of this arc. Now, there are three quarters of a circle here, right? There are three quarters of a circle, right? Because of these three quarters of a circle here, the angle at the center will be actually 270 degree, right? Or we can say the net magnetic field because of this arc will be three times the quarter of a circle. That will be three times mu naught I upon 8 r, right? Three times mu naught I upon 8 r, right? Now talking about the direction of this current, now there are two lengths here, right? There are two lengths. One is this one, another is this one, which are connected to each other, right? I can see here the angle. This is a length, right? This is a wire of length. Let's suppose L, which is carrying some current I, right? We know according to Biot-Savart law, dB for a current carrying wire, it's mu naught I dl sin theta upon R square, right? R square, right? 4 pi R square, right? Mu naught ideal sin theta upon 4 pi R square. Now, theta here is the angle between the current element and the line joining the point where magnetic field has to be calculated, right? Now, if we join this line with this point O, right? We can see here these 2 points and this line are actually along the same direction, or we can say the angle between them is actually 0 degree. So theta in this case will be 0 degree for these lines. So if theta is equal to 0, the magnetic field has to be 0, right? So any line which is passing through the point where magnetic field has to be calculated, then the magnetic field at that point has to be equal to 0, because the angle between the point and the line joining the current element at that point will always be equal to 0 degree. So the magnetic field has to be 0, right? So these two lines actually, these two segments will not actually, line segments will not actually contribute, right? So these two segments will not actually contribute to the magnetic field, because of these two wires will be equal to 0. So we'll be left with only the magnetic field due to this arc, right? And the magnetic field due to this arc. Now calculating the direction, right? Calculating the direction. You can see here the direction because of these both arcs are actually because of this these both arcs are actually in the downward direction, or we can say into the plane of this paper, right? Because of this both arcs, right? Perpendicular to the plane and into the plane, right? So this will be the net direction of the magnetic field, right? If we use the right hand thumb rule, right? Right hand thumb rule, we'll get the direction of the magnetic field into the plane of this paper at this point O, right? It means that both the magnetic fields will be along the same direction. So B net will be mu naught I upon. Now, for a second wire, right? For this wire, the radius is A. For the first wire, the radius is B, right? So we can write here is radius equal to A, and for the second wire, the radius is B, right? It's 8B. So it will be mu naught I upon 8B plus 3 mu naught I upon 8A, right? So from here, we can take mu naught I upon 8 as common. So it will be 1 by B plus 3 by A, right? 3 by A. So this will be the net magnetic field at this point O, right? Because of these two wires, right? Or because of these two arcs. Now we have a similar question here, right? Question number 9. The question number 9 says that a long wire bent as shown in the figure, right? We have a long wire bent as shown in the figure carries current I if the radius of the semicircular portion is A, if the radius of the semicircular portion is A, then find the magnetic induction at the center, right? Now we calculate the magnetic field due to a complete circle. Now let's see what is the magnetic field due to the semicircle, right? We know that a semicircle is also an arc, right? It's also an arc subtending an angle of 180 degree at the center, right? We know that magnetic field due to an arc is nothing that's mu naught I alpha upon 4 pi r, right? 4 pi r. Now here semicircular arc is subtending an angle of 180 degree or an angle of pi, right? We can say here the alpha has got the value equal to pi for this case. So mu naught I times pi upon 4 pi r, right? 4 pi r. Pi and pi will get cancelled. We'll be left with mu naught I upon 4 r. So this is the magnetic field due to a semicircle or semicircular wire carrying current I at the center of this circle, right? So, and at the center of the circle, that's at the point C here in this case, right? So here in this case, you can see the magnetic field at the center will be mu naught I upon 4r, right? Mu naught I upon 4r. Now there are two more wires, right? Semi-infinite wires which are carrying current, I, right? The current I enters this circuit, right? And the current I leaves this circuit, right? We have to calculate the net magnetic field due to these current carrying wires as well, right? Now at this point A, you can see here there are two ends of this wires, right? There are two ends of this wire, right? The direction of the magnetic field, because of this wire at this point, right? Because of this wire at this point will be, now you can see here the net magnitude of the net magnitude of the magnetic field at this point C. We can calculate here the net magnitude will be, so it's a semi-infinite, right? Semi-infinite. The angle subtended by this end of this wire at this point A will be 0, right? So sine 0 will be 0. So because of the semi-infinite, the net magnetic field will be mu naught I upon, it will be 4 pi d, right? 4 pi d, right? 4 pi d mu naught I upon 4 pi d will be the magnetic field because of this semi-infinite wire, right? Now talking about the net direction, right? Net direction of this magnetic field, right? Net direction of this magnetic field. I can see at this point, uh, if this is the wire, right? If this is the wire, then the direction of this magnetic field at this point will be given by the direction of the right hand thumb rule, right? So you point out the thumb along the direction of this wire, right? Along the direction of this wire, right? Then the direction of the palm will give us the direction of the magnetic field at this center of this coil, right? And similarly for this second wire also, if we direct the thumb of our right hand along the direction of the current, then the direction of the palm will give us the direction of the magnetic field at the center C, right? And because of this wire also, the magnetic field, let's suppose this is B1, this is B2, and this is B3. Now this B3 will also be B3 will also be equal to mu naught I upon 4 pi d, right? Mu naught I upon 4 pi d, right? So the net magnetic field at this point will be nothing, that will be B vector, that will be B1 vector plus B2 vector plus B3 vector, right? So these are the three magnetic fields. Upon adding will give us the net magnetic field. We know the value of P1, we know the value of P2, and we know the value of P3 as well. We can substitute the value of P1, P2, P3 in this equation to calculate the net magnetic field, right? So at this point, now here you can see here the value of R is given as the value of R is given as that's the value of R is A. We can replace here R with A, right? And D can also be replaced with A, right? So adding all these three fields will give us the resultant field at this point C, right? Now moving on to the next question, question number 10, right? The radius of a current carrying coil is R. The ratio of magnetic field at an axial point, which is 3r distance away from the center of the coil, to the magnetic field at the center of the coil, right? Now let's suppose this is the coil, right? This is the coil. This is the coil of radius R. This is the coil of radius R. and this coil is carrying a current I, right? This coil is carrying a current I. Then the magnetic field at the center of this coil will be mu naught I upon 2r, right? Mu naught I upon 2r. But the magnetic field along the axis at some distance x, right? At some distance x at point P, the magnetic field on its axis, that's axial magnetic field, will be given as mu naught I r square upon 2, right? R square plus x square raised to power 3 by 2, right? So this will be the net magnetic field because of this current carrying wire, right? Current carrying loop on its axis, right? So the net magnetic field here is mu naught I r square upon 2, r square plus x square raised to power 3 by 2, right? Now we can write this equation, we can modify this equation in terms of the magnetic field at the center, right? So P axial will be nothing. What we can do here is that we can just take r square as common here, right? We take r square as common, so it will be mu naught r square upon 2 r square, right? So it will be r cube here, right? It will be r cube. It will be 1 plus x square upon r square to the power 3 by 2, right? The power 3 by 2. Now from here r square and r cube will get cancelled, right? So we'll be left with mu naught I upon 2r multiplied by 1 plus x square upon r square to the power 3 by 2, right? 3 by 2. Now we can replace this mu naught I upon 2r with this B center, right? B center. So B axial is nothing. It will be T center upon 1 plus x square upon r square whole power 3 by 2. So this is the net magnetic field at this axial point, right? This is the net magnetic field at the axial point, right? This is the net magnetic field at the axial point, right? In terms of the magnetic field at the center, so, right? So now the question is the ratio of magnetic field at an axial point, which is 3r distance away from the center of the coil to the magnetic field at the center, right? So we have to find this ratio. So P axial upon P center from this equation will be nothing. It will be equal to 1 upon 1 plus x square upon r square to the power 3 by 2, right? To the power 3 by 2. Now the value of x here is given as that's equal to 3r, right? That's the value of x. We can substitute the value of x here in this equation to get the final solution. That will be 1 plus 3r square will be 9r square upon r square, right? To the power 3 by 2, right? 3 by 2. Or from here, it will be 1 upon 10 to the power 3 by 2. This will be the ratio, right? This will be the ratio between the two magnetic fields at a distance of 3r from the axial, at the axial point from the center of this circular loop, right? So this is how we can find the ratio between the magnetic field at the center and the magnetic field at the axis of a current carrying loop. Now let's move on to the next question, right? The question is about the magnetic field as a magnetic field to a solid cylinder, right? So we'll be explaining a bit about the Ampere's circuit law here, right? So Ampere's circuit law says that closed line integral of the magnetic field, right? Closed line integral of a magnetic field, right? That's integral of B dot dl. It will be always equal to mu naught I enclosed, right? Mu naught I enclosed. So this is how we use the Ampere's circuit law to calculate the magnetic field due to different objects, right? We can use the magnetic Ampere's law to calculate the magnetic field to different objects. We can use it for the cylinder. We can use it for wire as well, right? So we'll be using this law, Ampere's circuit law, to calculate the magnetic field due to cylindrical wire of radius r, right? Now let's suppose we have a cylindrical wire, right? This is the cylindrical wire, right? Of radius capital R, right? Of radius capital R. This is the cylindrical wire of radius capital R, right? The net radius of this wire is capital R, right? The radius of this wire is capital R, right? Now we have to find the magnetic field at the external point, right? At some external point as well as inside the cylinder, right? Now let's suppose the external point where we have to find the magnetic field is at a distance of p, right? At a distance of p, at a distance of p, right? Now at this external point, we have to find the magnetic field, right? We will draw an Amperian loop at this external point, right? Drawing an Amperian loop, right? Let's suppose this is the Amperian loop, right? Of distance r, right? And at each and every point on this Amperian loop, the magnitude of the magnetic field is a constant, right? The magnitude of the magnetic field is a constant, and here on this point, the direction of this current element is along the direction of the magnetic field, right? The direction of this element dl will be along the direction of the magnetic field b, or we can say the angle between magnetic field vector and dl vector will be 0, or we can say integral of b dot dl will be integral of p dl only, right? And the magnitude of magnetic field at each and every point on this Amperian loop will be a constant here, right? So it means that we can take this b outside integral, right? That will be integral of dl, that will be equal to mu naught I enclosed. The I will be the total current enclosed by this Amperian loop. That will be the total current flowing through this cylinder. That's I, right? So P here will be nothing. It will be mu naught I upon 2 pi r, right? Mu naught I upon 2 pi r. So this is the net magnetic field, or we can say B is inversely proportional to the distance r at a point which is outside the cylinder, right? At a point which is outside the cylinder, right? Similarly, if we have to find the magnetic field inside the cylinder, now the magnetic field in this inside the cylinder will be a different magnetic field, because inside cylinder for different Amperian loops, the enclosed current will be a different current, right? It will be a different current, right? So let's suppose at a distance of r, we have to find from the center of the cylinder, we have to find the magnetic field, right? At a distance far from the center of the cylinder, we have to find the magnetic field. So what we'll do here is we'll once again draw the Amperian loop of radius r, right? We'll draw the Amperian loop of radius r. Now along this through this Amperian loop, we have to calculate the current enclosed, right? Current enclosed. Let's suppose a uniform this cylinder has a uniform current density right through it, right? And the current density will be nothing. It will be I upon pi capital R square. This will be the current density through this cylinder. Now this current density should be a constant, right? Should be a constant or uniform current density. Now the current density through this Amperian loop, which is inside the cylinder, will be, let's suppose I enclosed upon pi small r square, right? So from here pi and pi will get cancelled. We will get the value of I enclosed here. I enclosed will be nothing. It will be I times r square upon capital R square, right? R square, I times R square upon capital R square. So this is the current enclosed by this Amperian loop inside the cylinder, right? Now once again applying the Ampere circuit law, that will be integral of B dot dl, right? Integral of B dot dl will be equal to, it has to be equal to, integral of B dot dl will be equal to mu naught I enclosed, right? It will be mu naught I enclosed. That's integral of B dot dl, right? So mu naught I enclosed will be the value of I enclosed here is nothing. That's mu naught times I small r square upon the capital R square, right? This is the enclosed current in this Amperian loop. Now here once again this the direction of the magnetic field because of this current I, because of this solid cylinder, the magnetic fields will be closed loops, right? The magnetic field lines will be a closed loops, right? They will be a closed loop. It means that the magnetic closed loop will actually fall on this Amperian loop, or we can say the direction of the magnetic field will be along the direction of this length element, right, on this Amperian loop, or we can say the direction of, or the angle between the magnetic field on this loop and the angle between the length element dl will be equal to 0 degree, because the magnetic field will be along the direction or tangential to this Amperian loop, right? So the angle between b and dl will always be equal to 0 degree. So it means that we can replace this b dot dl with b dl, right? B dl. Now b is a constant on this Amperian loop. At each and every point on this Amperian loop, the magnitude of the magnetic field will be a constant, right? So we'll just take b outside this integral. It will be b integral of dl, that will be mu naught I small r square upon capital R square. Now integral of dl will give us the circumference of this Amperian loop, right? The circumference of this Amperian loop is 2 pi r. So from here, so b multiplied by 2 pi r will be equal to mu naught I r square upon capital R square, right? So from here R and R will get cancelled. We'll be left with the magnetic field as mu naught I into R upon 2 pi R square, right? So this is the net magnetic field due to solid cylindrical wire inside it. So if we plot the graph between the magnetic field inside the cylinder and magnetic field outside the cylinder, right? Now let's draw the graph, right? This is the magnetic field as a distance, as a function of distance r, right? Now inside the cylinder, magnetic field is proportional to the distance r, and it will become maximum at the surface of the cylinder, right? At the surface of the cylinder, right? So this is the maximum point. Then magnetic field will start decreasing, right? As 1 by r, right? As 1 by r. So here b is proportional to r, right? And here b is proportional to 1 by r, right? So this is the variation of the magnetic field inside the cylinder, right? Now we have to calculate the ratio of magnetic fields at a point which are located at r by 2, which is inside the cylinder, and 3r distance away from the axis, right? So at r by 2, so we'll conclude all these calculations with two equations, right? We'll conclude it with two equations only. That's the magnetic field inside the cylinder and the magnetic field outside the cylinder, right? Now the magnetic field inside the cylinder is nothing, it's mu naught I r upon 2 pi r square, or we can say it is proportional to the distance from the center of this cylindrical wire, right? So inside will be nothing, it will be mu naught I multiplied by small r upon 2 pi r square, right? Or we can say B is proportional to r, right? And similarly outside will be mu naught I upon 2 pi r 2 pi r, or we can say b outside is inversely proportional to r, right? So b inside is directly proportional to r, and b outside is inversely proportional to r. Now for the given question, the value of b outside will be at a distance of 3r, that will be mu naught I upon 6 by r, right? And for inside point at a distance of r by 2, right, it will be mu naught I into r by 2, right, upon 2 pi r square, right? 2 pi r square. So this and this will get cancelled. We'll be left with mu naught I upon 4 pi r, right? 4 pi r. So we have to calculate the ratio between them, right? We have to calculate the ratio between them. So b inside upon b outside we have to calculate. That will be equal to mu naught I upon 4 pi r, right? Multiplied by 6 pi r upon mu naught I, right? So this and this will get cancelled. Pi r and this will get cancelled. It will be nothing. P inside upon P outside will be equal to 3 by 2, right? 3 by 2. So this is the net magnetic field. This is the ratio between the magnetic field outside and inside and outside. Inside at a distance of r by 2 and outside at a distance of 3r, right? From the center of this cylinder, right? So this is how, these are the two important equations with respect to your exams, right? And this graph is also important graph, right? This is also an important graph to calculate the magnetic field due to cylinder inside as well as outside, right? So that's it for today, right? We'll be stopping here and we'll be starting with the magnetic field due to a moving charge in the next lecture. So till then, take care and goodbye.